So summarizing this study, we developed a 15-way approach towards classifying quantitative models. And in general, the trends observed in 1998 seem to be consistent through 2005. In informal feasibility studies, the assertions seem to be greatly declining. When I wrote this up about 2 or 3 years ago, the original paper appeared in 1998 in IEEE Computer Magazine. I thought that this was an important trend to mention, that this is a good sign for the field in general. And I decided Computer Magazine would be a good place to try to get it published because they published the original paper. I had an interesting history with that paper. First, it got rejected on the basis that the paper was too short. I never had that happen to me in my life, where they said, pad it with more stuff because it's too short to be published.
When was the first paper?
1998, May 1998. So, and they said, we don't accept paper. And all I wanted was a short paper saying, an update to the 98 paper, here's the trend is continuing, that's a good thing. And they said, too short. So we added more stuff, like, to get it published. And then about 6 months later, it was rejected a second time, saying, we already published it, we're not interested. And I found that strange because, yes, they published a paper, but to me, this is sort of confirmatory or, or more evidence that the trend is continuing. But we did get it published somewhere else. But I thought it was...
Well, if you're making a causal claim, one of the things is that the cause has to precede the effect. And if the paper was published in 1998, all of those trends, all of those trends had already happened by then, hadn't they?
Well, you just had 3 points, 85, 90, and 95. So we just had 3 points.
I mean, you're not claiming that the paper caused the trends. Because the paper...
No, I'm not.
No. Okay.
I'm just saying the trends, but we want to make sure will the trends continue. One of the confounding factors, in this study, is that the editors and the program committees of the objects we studied, of the journals and conferences we studied, all change every couple of years. And a lot of these, a lot of the criteria for acceptance depends upon who's sort of running the show, who's running the conference or running the journal. And you had different sets of editors. So we wanted to see, was it just some anomaly based upon, for example, here it actually got worse and then got better. So you can't say this trend means anything yet. So we felt, given that we had it at this point, we have 2 more points that look good. 2005 definitely is an improvement over 1995. 2000 is sort of an anomalous point based upon the other 4. Anyway, so we did want to get it published, and we did. And I would have accepted the fact that they didn't believe our data. But to say that we published it before is the reason, I think, is not right. There could be many reasons why they don't publish it, but not because we published it before. Anyway, so those are the trends. So in the software engineering world, at least, things seem to be going better. So now what? How do we generalize this to other sciences, and what can we expect from a scientific theory? So when you look at the evolution of scientific information, you typically go from concept to hypothesis generation to theory and to law. What's the definition? What's the difference between a theory and a law? I would claim that laws just have better publicists, better PR. There really is no, in science, there's no real difference. We talk about, we talk about the law, not so much theory of gravity, we talk about the laws of gravity. Well, it's just a theory. Just that if it's been a theory that's been around for a long, long time, we kind of make it more staid with the... No, there's no difference. Except laws have been around a long time.
Well, there's like Boyle's law and Charles' law for gases, but the real thing is like the kinetic theory of gases that explains all those laws.
But anyway, there's no real difference, but people like to use the word. Then we can talk about in the computer business Moore's law, which isn't even a law or a theory, it's just an observation. So the word law belongs in the legal profession. It really doesn't belong in science, really. Basically, science progresses this way. As I mentioned earlier, most of a scientist's time is really spent up here, trying to figure out what is the concept. and how do we sort of quantify it in some sort of model of the world. Then you can generate a hypothesis and go through the scientific method and just collect data and do everything else. But this is where the real work leads. What do you want in a scientific theory? You pretty much want at least these 4 attributes. Parsimony, you want to be able to explain a variety of phenomena with a short, coherent explanation, sort of a variant of Occam's razor. Occam's razor doesn't say that the shortest theory is always right, but it says you should look there first. Before you look at something complicated, look at something simple. If a simple thing explains something, stop there until it doesn't work. Then you look at more complicated things. You want generality. You want to permit a reduction in the number of independent phenomena with a single theory explaining a wide range of phenomena. The example I gave with complexity measures in programs, and I'm not kidding when I said I read a paper with like 76 measures of complexity. I find that a little bit mind-boggling because physicists like to describe the world in terms of 4 forces. Yet it takes 76 measures to explain a program, which is just a small part of the world. This seems to be inconsistency there. You can develop mathematics with a single operator. You don't need lots of operators. Yet why do you need? It seems like the 76 measures of programs is more like going to the epicycles of explaining how the planets worked when you didn't really understand it. So you had these complicated formulas for describing how the planets moved around the Earth, and became a much simpler system once you came up with, well, maybe the Earth moves around the sun, and that makes all the equations a lot simpler. We want prediction. And I mentioned earlier, what we want out of a theory is we want to anticipate future events, often to a high degree of accuracy. And we want explanatory theories, provide a compelling underlying mechanism that why should this happen? I found this slide by Paul Cohen, wrote a paper called Empirical Methods for Artificial Intelligence, which is an interesting way of looking at how scientific theories develop. We can talk about an empirical approach and a theoretical approach. And we can talk about a system-specific observation, like my computer here, general, all computers. Or I can look at a Windows machine by Microsoft, Windows operating system by Microsoft, or maybe general. It covers Windows and Macs and Linux systems and all kinds of operating systems. And typically we start very empirical, like my system has this properties, and we try to get very general. And we want to get more theoretical so that we could generate properties or observations about any kind of system. And models typically are descriptive. What does the system look like now? They can be predictive, what's going to happen in the future, or explanatory. Not only can we predict them, but how can we explain them? Well, looking at the software engineering world, we've been stuck in the computer science world, we've been pretty much stuck in this quadrant, this corner, for pretty much the last 30 years. We have very few predictive models. There's been a fair amount of work looking at cost estimation. If you're a company that wants to build a new product and you have to do a proposal, the typical way of coming up with a cost estimate is you find out how much the company has to spend, and that's what you bid. But if you want to decide what's really going to cost you, there are some techniques for figuring out what you think it's going to cost to get that product built. So there's a little bit of prediction in some of these models. They don't work great, but there is some. But the problem with predictive models is it might be something it's 10 times the number of 1,000 lines of code raised to the 1.02 power. Well, explanatory model would say, what does the 10 to the 1.02 mean? Why isn't it 10 to the 1.37 or 10 to the 0.96 power or something? So the exponent, if you can explain the exponent, that gives you more of an explanatory model. Just putting in that exponent gives you a predictive model that you can use. And you'd like to know explanatory, why is it such and such?